Good evening, ladies and gentlemen. My name is Ishan Datta, and today I'm not here to give a talk. I'm just here to perform a bunch of magic tricks. I'm sorry, organizers. I'm not an AI researcher. I'm just a magician. I was looking for an international stage. This is the stage. You all have been pranked, and this is not an AI talk. Or is it? Am I saying the truth or not? To find that out, we have to go back a couple of years and listen to a story. 4.5 years ago, I was in my sophomore year of my college, this is the second year, and I got a call from someone very high at a very high rank at Amazon US. That was my day zero in AI, and what she explained me is the kind of algorithms and the kind of problems that they are solving at Amazon at the very core level with the help of AI. Throughout that 2-hour conversation on call that I had, I was left with one question. Is this magic? So you are telling me that I give you a bunch of data, you have something called as a model, and once that model is trained, you can predict things. And you can even predict things that are in the future. If that is not magic, what is it? Since the last 4.5 years, I have been on the quest into finding the answers of what is this magic? What are the tricks behind this magic? And who are these magicians? A brief introduction about myself. As of today, I work as a machine learning engineer too in the core generative AI team of Adobe India. Along with that, I have freelance contracts with two very popular startups. One is Lightning AI, and another one is a vector database startup called as LanceDB. I also represent Jarvis Labs AI as a global brand ambassador. Previously, I have worked with the likes of NVIDIA, Weights and Biases SF, as well as a bunch of research institutes like Indian Institute of Technology, Kanpur. I'm also a Kaggle Notebooks Master, top 70 in the world, and I have a bunch of top ranks in multiple hackathons. If you want to follow me on my socials, feel free to scan the QR. Introducing you, magician diffusion. Think of this example. Who is a magician? What is a magic trick? Any magician who is there, he gets a number of props. He learns to how to use these props in the best way possible. He iterates over that trick multiple number of times and gives out what is called a performance. If you relate it to the world of AI, those props are actually the data set that you're providing to the model. The model is actual magician who iterates over this data multiple number of times unless he understands what to do with it. And the kind of output the model provides is the result that is there in terms of magician, is the performance that you're going to see. Now, before we actually look onto what are these tricks that the magician diffusion uses to bring such beautiful outputs, let us see what are the outputs that we are talking about. What are diffusion models actually able to do? I have two examples over here. The first one is a very popular text to image generation. We have a bunch of open source models now, and they are doing really, really good. These images are from DALL-E, by the way. A second very popular use case came out very recently by OpenAI, which is called as Sora. This is one frame generated from their text to video model. And the kind of bunch of tricks which he does not reveal very much. Right. Now, these tricks are what make the magic tricks magic work. Every algorithm, you can think of it as a magician. Every algorithm has a bunch of particular concepts which it uses, which makes it unique, and so that it can produce a particular output. Today in this talk, I'm going to focus on 3 important tricks or 3 important concepts behind diffusion models, which make it work and make it get the kind of outputs which you saw over here. Before we go into the tricks, I will introduce you diffusion models, how they are trained, what they are, and a very brief overview. Then we will dive a lot deeper into it to keep the topic deep dive into diffusion models as it was originally. Now, in the case of diffusion models, think of it this way. I give you a perfectly good painting of a very beautiful view of Hanoi, right? And I give you a task that, let us see, you have 10 seconds. Every second, you can pick a couple of colors and you can put a couple of brush strokes on that painting randomly. You do that for 10 seconds, 10 number of times. And at the end of it, you will have a completely random canvas with random colors because you have been putting random colors over it. In this case, in the first image that you are seeing, you have a perfectly clear image. In every time step, for now, let us take the analogy that every time step is equal to 1 second. This is the image at the 0th second. At the first second, I add some bit of noise to it. At the second, again, some bit of noise. We continue it throughout to t time steps. For this example, let us say we are running it for 10 seconds. So at the 10th second, we have something which looks completely like noise. In the kind of painting analogy, you have just random colors on the canvas. You cannot make out what it is. In the reverse process, what we have to do is that given this noisy image, I have to figure out a way so that I can come back directly to this good image. It's like you have a random color canvas painted, and you have to undo the entire process which you did. And from just some random colors on a painting canvas, you have to go back to a perfectly good looking picture, right? This is very straightforward. Pick an image, add some noise to it progressively, and then again in the reverse process, the name itself is reverse process, you reverse the entire thing. Now there will be a bunch of questions which will be in your mind. The first one should be, before that, I will tell you a little, give you some bit of mathematical notations. These will help us with a bunch of formulas that will be come up ahead. Now, if you are scared of math, don't worry. I will try my best to keep these things as simple as possible. Diffusion models has, I believe, the most amount of math any AI algorithm has had. I have derived equations, handwritten equations of over 200 pages and all, just to complete this entire presentation. I will show you some of those derivations, but not all of that is possible in 25 minutes for sure. So very simple, it's very basic. You have the original image. Okay, we represent images with the variable x. Since this is the first image, we are computer science engineers, we will give that a 0 and not a 1. So x0 is the first image that we have. We go for t time steps. In our example, t, yeah. If our example t, since we are starting with 0, in our example, t capital T will be 9. Okay, so we go from 0th second to 9th second. In the 9th second, we have completely noise. In the reverse process, we are again starting from the completely noisy image. At the 9th second, we go back and reach the original image. That is it that we are doing overall. Now the tricks that are behind this, there are a bunch of them. The first thing that should come to your mind is that, Ishan, I'm adding noise gradually to it, right? Why not just pick an image, add completely noise to it, and then learn a mapping which can learn from generating image from that noise? Why do you have to go in steps? You can just learn one mathematical function which is complex enough that can convert any noise into an image. What is the need of going in steps? The second one is called as a noise schedule. So let's come back to that later. And the third one is called reparameterization. Now, most of these tricks are relevant more towards the forward process, okay, and the reverse process as well. To understand why we are taking steps, think of this example. Let us say you have gone on a vacation. Like for me, this is also a kind of vacation. This is my first time in Vietnam. So I'm staying in a hotel. Now, I look for a couple of restaurants nearby to have some good food and some good Vietnamese cuisine. You guys have lovely food over here. Thanks a lot for this. And I find this restaurant, which is at the other side of the street. Okay. Now, there are a bunch of ways to reach to that restaurant. The first one is that I think of it that I am staying here. These are all roads, by the way, and I can reach somehow directly to that restaurant. Is this path actually possible? The one which I have drawn. Is this possible or you can just nod your heads if you think it is not possible, right? Think of it a second. See, this talk is also here to develop your intuition behind why these algorithms work. I have seen a lot of blogs, I have seen a lot of YouTube videos on this, and I have seen very few people try to give out intuition behind why things actually work instead of just like putting out formulas that they are there. This is not possible because if you think what makes you say this is not possible, it's your brain telling you that it finds no way to calculate a way that it can make you reach directly from that road to here because there are corners. You cannot jump from here to here. So your brain actually calculated this for you and told you this is not possible. If I change this path a little and I give you this path, so you are here, I give you step-by-step directions. You go straight, take a left, again go straight, take a left, and again go straight. Is this possible or not? It is right. Why? Because I gave you smaller steps, your brain is now able to calculate, okay, I'm standing here, I have to go there, then I have to take a left, then I have to take a right, and it is more calculatable by your brain. In terms of machine learning and statistics, we call this as tractability. Tractability is when something you can actually calculate using your machines. The last example was intractable. We cannot calculate away. This is tractable because we are going in small steps. In the case of our processes, that is the main reason that we are doing it. If I turn a completely good image into completely noise and try to go back directly, just without taking any steps, just in one time step, that is an intractable process. There is no way you can calculate something which is capable of doing that. That is the reason, and that is the first trick which magician diffusion uses. The second thing is called as a noise schedule. So when I tell you that I add noise in different steps, you might think of, okay, but what is the amount of noise that I'm adding? It's like if I'm giving you the painting example, you have perfectly good painting, and I give you one brush and a bunch of random colors. So how many brush strokes am I allowed to actually paint in every time step? Is it 5? Can I do 10 brush strokes? Can I just throw a bucket of painting on the picture, right? How many of it? So there has to be a way that we make it actually calculatable. The first authors of this comes from the paper, Denoising Diffusion, Probabilistic Models. The terms are very heavy, but when I break it down to you, it will be okay. Very, very simple. It's denoising because you're basically removing noise. Okay, it's diffusion, and we will come to that later. The first method that they came up was with increasing things linearly. So let us say I allow you that for the first time step, you can add 2 brush strokes. For the second time step, you can add 4 brush strokes. And you can go on and go forth till 20 brush strokes. And your graph will look something like this. Okay, it's a linear graph, you're linearly increasing it. But there is a very big problem with that. If you see this image clearly, so you have a dog over here, very cute looking dog. Until we are close to 40-50%, doesn't this already look like completely noise? It does, right? Is there any point of going from here to here? No, right? It's like when you're taking a Grab taxi, you have already reached your destination, but the driver wants to increase your fare, so he will just make you go circle round and round and round, so that the fare increases, but you're actually at the same place. So that travel is not taking you anywhere, right? Because of that problem, the authors of OpenAI came up with a different paper, which is very critically called as Improving Denoising Diffusion Probabilistic Models. Okay, and what they did was they came up with a cosine function, and a cosine function helps you with gradually increasing the noise. If you compare it picture by picture, you can see that the kind of dog that you can see here is a little more clear than the picture that was there. Okay, now this makes that step-by-step thinking even better for the model, and we are completely going to noise here. The major advantage of this was, in this case, the original authors had to take 1,000 time steps to reach that noise. With this method, you can do it in just 50 time steps. That's an amazing efficiency. So noise schedules are the second interesting trick that diffusion models use. Now remember, we represent noise schedules with the term beta. Okay, beta, because we will come to that later. Now to understand the third and an extremely important trick, which is called as the reparameterization trick, we have to understand the math behind diffusion models a little more. I know everyone might not have the same math background, And so I'm going, the formulas will be there, but I will explain it in a way that you can understand what that formula means instead of going like line by line what it is doing. So the forward process was this: you're just adding noise step by step until you get a completely noisy image, right? So this is how the forward process is represented. So if you have to give a variable, so at every time step, what am I doing essentially? Think of it like this. I have an image, I pass it to something, it adds some noise to it and gives me another image. Okay, that output becomes the input for the next time step, right? And so on and so forth, we are going till the end. This can be represented in this way. So at t, let us say t is equal to 3 over here. Okay, so t minus 1 is 2. I give the output at the t at 2 seconds, okay, whatever image I have after adding noise at 2 seconds. And I want something, a process, let us say q represents the forward process. I will pass it to q and it should give me x at 3. I'm giving a previous image, I get the current image. So the kind of noise that we add is called as Gaussian noise. Gaussian noise is a very interesting kind of noise. I will show you the graph and why exactly we are adding it. But to understand this notation, this looks very big. It is extremely simpler. And the authors have made a lot of things constant, so you don't have to worry about it. To understand the notation, this is the actual symbol for Gaussian noise. I call it the stylish n. And you have x of t, the output. So if I am at t equal to 3 seconds, I'm getting t equal to 3 seconds output with the picture I had at t equal to 2. Okay. Now, this is called the mean and the variance. So to understand what are mean and variances, let us say the average age of people in Vietnam here is 33 years old. Okay. What is the meaning of average or mean? Okay. Think of it a little more. Let us say I have a number line from 0 to 100 and you have divisions of 1 year each. Okay, 0, 1, 2, 3, 4. When I say that the average age of people in Vietnam is 33, it means that since this is a college, the number will be different. But in general, in the entire country, if I ask someone, there is a very high chance that their age might lie somewhere very close to that number 33, right? So if you imagine that kind of number line, you will see that a lot of points are actually concentrating close to that number 33. So that is the mean of a distribution. Everything in the world is a pattern. Your age, where you are coming from, okay, what you're learning, what you're reading, even your daily schedule is actually a pattern. And machine learning is all about recognizing those patterns. Okay, now that is the mean. Okay, you understand what mean means. Variance is basically how far does it spread. So if you think, let us say this is the number line, you have 0 to 100, and here somewhere you had that 33. Most of the points lie here, but how far do those points lie? Okay, that gives you a variance. If the variance is very small, most of the parts will lie close to the mean. If the variance is very high, most of the parts will lie very far from the mean. That is the kind. I will show you the graphs as well. But for now, this is the mean. Beta, I had told you the noise schedules that were there. So beta is the amount of noise that you are adding at every time step. T, okay, and beta t of I. This is variance. Anyways, this becomes constant later, so you don't need to worry about that for now. Now let us think of what is actually happening. So we say we are using the term Q to represent one step of the forward process. As defined earlier, x of 0 is the first original image that we have. We pass it to something, which is a forward process, to Q1, okay, and we get that image at time t equal to 1, and we do that n number of times, right? So it's like a function of function of function, finally till we reach Q of t, okay? That is that at Q of capital T we are reaching. Now, if you try to see this as just with one time step, let us say I'm at the first image x of 0, and I want the next image, which is at first second. Okay. The formula will look like this. The output is x of 1. In the mean, we have beta 1 and x of 0. And in the variance, we have beta 1 of I. Okay. Now notice these two terms very carefully. I is identity matrix by the way. It is completely, you can imagine it as a diagonal matrix. It's completely ones. So it's a constant. Now, if you go to the next step, where we have the image from the t equal to 1 second, and we want to calculate the image at t equal to 2 seconds, we have output x of 2, we have beta 2, we have x1 here, and beta 2i. There is a very interesting thing, and there is a pattern over here. Okay, the pattern is that these two terms, if you see beta 1 of I and beta 2 of I, you already know I. It's just a matrix, which a bunch of ones arranged diagonally. Okay. Betas is something which we have already calculated because we have a fixed formula for it. So this becomes a constant. Kick it out. We are now just concerned about the mean. Okay. Now the authors added a bunch of more notations to it. I will tell you the reason why. Now, if I tell you that I have to go for 1,000 time steps, so every time I'm doing a training loop, okay, and let's say in this training loop, I am at the 500th second. So I have to add that noise 500 times to reach that particular output. Let's say in the next training step, I am at 501st second. So I have, okay, so I have to add that, that number of times. So to solve for that, the authors came up with more notations. You can replace alpha t with 1 minus beta t, and you can have the product of all alphas from 1 to the last time t as alpha hat of t. If you replace that, okay, I replaced alpha t with 1 minus beta t in all of it. And finally, the mean of that equation was this. And you can just go to t minus 2, t minus 3. The final output which you will get is that alpha t bar of x naught. Now, what is the benefit of this? Is that now this equation is represented in this way. Okay, you see 1 minus alpha t is gone. This we will find out how to get it, but this is x naught. So the benefit of this equation is that now I can give this equation any t, because this is dependent on x0 only, and I can get the output. So if my training loop, let us say it wants the image at t equal to 500, I don't need to go for 500 steps. I have a formula which will give me the image at the 500th step. That makes it super, super efficient. Okay, but there is a very big problem with this. This is not, you cannot calculate the derivative for this. Okay. You will say that, wait, man, you have been talking about Gaussian distributions, but if you can't use it, if the neural network can't use this to walk, it's like I gave you a path, but that path does not, you cannot go to that path. Okay, it's like, let us say you're trying to learn a new recipe. Okay, and I give you 5 ingredients from a shelf with 1,000 ingredients, and you have to learn to make a recipe. Now, the way to go about it is that you try different ingredients, you replace 1 or 2 of them with different ingredients and see what works and what does not. If every time I'm giving you 5 completely random ingredients, will there ever be a day that you will be able to reach to the correct recipe or not? There won't be. Because you won't know that because of which ingredient, I am very far from that recipe. So that is the same thing which happens over here. If you are just pulling it random examples from the distributions, you won't actually reach anywhere. So what is the reparameterization trick? Is that if you have a standard normal distribution, okay, with a mean of 0, okay, I talked about that graph before. There's a mean of 0 and variance of 1. If you see these graphs, all of these have been derived from this. Okay, how? You see, in these 3 things, in these 3 graphs, the mean is mu represents the mean, sigma square represents the variance. The mean is the same, 0, but we have just moved the variance. So it has become wider. Okay, if I have changed the mean from 0 to -2, it has moved towards the left. So what you can think here is, if you are actually adding or subtracting something to the mean, you can move it, the graph left or right. And if you are actually multiplying something with the variance, you can make it smaller or larger. So that is the final reparameterization trick that you have, where you can actually, you have the mean and you have the variance. You keep the mean as it is. And instead of actually using that distribution, you can just multiply something with the variance. So using just that one graph where you already know the mean and variance, you can find this as a product form. Now this is computable. Why? Because in this case, these are 2 random. Okay, you're every step you're pulling this randomly. This is like random ingredients that you are pulling for the food, and you are trying to process it. You cannot come back to it. But I have kept the randomness out of it. That is epsilon. So now this derivative can be computed. Okay. Now I think we are a little out of time. So I will, yeah, this is fine. I will give you a very brief. Okay, I will give you the very brief of the reverse process. What actually we do. Actually, we can just go directly to this one, training and sampling, how that happens. Yeah, we have 2 minutes actually. No worries. Anyway, whatever tricks I told you, the same will be applied over here. In the reverse process, I had a bunch of formulas, but anyways, you will need the derivation for this. But the training algorithm is very, very smart. The training happens in actually 2 ways. The first way, you take an image from the data set that you have. Okay, you take any time step from a uniform distribution. Okay, any time step, I gave you a formula on which you can get the image from any time step that is possible. And you take epsilon. Epsilon represents the noise from a normal distribution. And then what the actual model tries to learn is that the noise which I have added, okay, can I remove that noise? So it is actually trying to predict the noise which was added in that time step and to try to remove that noise. That is something which is it trying to reduce. So it does that till n number of steps, okay, till it learns how to remove noise from that particular image and that particular time step. And in the final step, we have something called as sampling. So once you have learned a model which is capable of removing noise, then what you can do is you sample any random. So this x of t is sampled from a normal distribution. This is just random noise. Okay, you go from capital T towards 1, and you repeat it like till you reach 1. You have, and then using this formula, you can actually calculate how to go for the x of t minus 1. I couldn't cover that because of the time. Yeah, but this is it. And yeah, that's it. So training is basically you first train a model which learns how to remove the noise. And secondly, you use that model to pick any random noise and make a very clear picture out of it. Thank you everyone for listening. And now that you know the magic tricks, you can learn to start the magic. If you want to follow me on my socials, this is the QR code. Anyone has any doubts or questions, you can ask me separately.